Hello and welcome to the 16th part of the tutorial on writing your own operating system. In this tutorial we will talk about the heap and dynamic memory management. Because right now we have allocated everything very statically. In some functions we just have these objects and they are allocated on the stack. Sometimes you just don't know in advance what memory you need. For example, when you iterate through the PCI devices and you find a device that so you find a device and then you need to instantiate a driver, or you need to reserve some space for the driver. And then, of course, you need to keep track of the space that you have already assigned to something, because you don't want things to overlap and disturb each other. Okay, so what I'm going to do is actually quite easy. So if you've had lectures on data structures, if you know linked lists, this won't be very surprising for you. So here's your RAM, and we've talked about this before. So you have your video memory, the memory for your text, then the BIOS is loaded somewhere. The BIOS has loaded the bootloader. The bootloader has loaded the kernel, and the kernel has its stack. And then after that, there is a lot of nice free space that we can use. So we can assign this and use this any way we want. Although I'm not really sure, I haven't found a way to find out if grub has put something behind the kernel. It might have written something here. So, for example, the multi-boot structure, which we will talk about later again. We don't know where it is. It might have loaded modules. They might be behind the kernel. We really don't know how much space there is. And as I've said, I haven't found a good way to find that out. So what I'm going to do is I will just take the pointer to the stack, and then I will just add something like, 4 megabytes to it. And hopefully that is enough so that we don't overwrite anything in there. So this is also actually a method that where was it? I'm not sure if it was on OSDev or Low Level EU. They really said that this is the way you should do it. You should. They advised you to really take a fixed offset and say everything behind that belongs to me. If you ask me, there really should be a better way. Grub should tell us where it put the last data, but as I've said, maybe there is some way to find this, but I haven't found a way to ask for this. And I've really given up on the topic, so this is really how I'm going to do it, although I don't like it. So how will we do this? Don't I have a better pen? So how are we going to do this? As I've said, this is really very similar to a linked list. So we will make a class called memory manager and give it this pointer and then some size. This size at least we can get from grub. But yeah, so then we are over here. And what I'm just going to do is I will write a class memory chunk, which is supposed to have a pointer to the next memory chunk and the previous memory chunk. Then a Boolean, which tells us if it is allocated. And the size t for the size. I think size t we haven't defined yet, but this is really common practice. I will just put that into the types.h. So such a memory chunk really describes, the memory manager will be responsible for handling the space over here. Okay, so this is the space it's responsible for. And then we will ask the memory manager, hey, give me 1024 bytes. Okay, and then it's supposed to find some area in the RAM that is large enough and give us a pointer to it. Okay, and these memory chunks are basically a linked list. Double linked, actually. And okay, this won't be a fast implementation, but for every chunk that we've cropped from the RAM, we will have an entry in this list. Which correspond to, so this is how we keep track of the data that we have already used and the data that is free. But the question arises, where do we put these values? I mean, when you do a linked list in the data structures lecture, you just say, hey, I want to allocate a new node. Yeah, but we can't do this here, because here we are currently writing the code for give me a new node, right? So we cannot say, hey, I want a new memory chunk, because we are writing the thing that gives us the response to that. Okay, so we need to think about how to decide where to put these objects. So we have to manage that really manually. But the thing is, we have a lot of RAM here. Okay, so we will just use the RAM here for this list. Okay, and many people prefer to put just some table at the beginning of this area and keep track of things in this table. I will do it like this. I will put these objects just at the beginning of these chunks. Okay. So if you request 1024 bytes, then I will actually chop off 1024 plus size of memory chunk. Okay? So then we have the next pointer, the previous pointer, the info if it's allocated, and the size. Okay. And as a convention, I will just have the size be the size of the data that is actually used here. So if I allocate 1024, then there will be a 1024 in here, although this is more than 1024. Okay, so the size is only telling us how much data is behind that chunk, behind that header. Okay? And then I want these pointers here in a linear order. So the next pointer is going to the next entry, and the previous pointer is going to the previous entry. So the next pointer is going to be to the chunk that has the smallest offset larger than this one's. Okay? So these pointers will never cross each other. Okay? You will not have a pointer to a chunk over here and that has a pointer back here or something. This will always be in a linear order. Okay. This isn't hard, I think. One thing that I want to mention, when we free the memory again, if we deallocate it, let's say this chunk here is free. This one has been allocated, so there was a 1 here, and say this one is also free. So if I just set this allocated to false, this is somehow stupid, because say if I have 1024 here, 1024 here, and 1024 here, and now I try to allocate something like 2100 or 2500, then it would come here, see, okay, the size is too small, this size is too small, I'll continue, this size is too small, I continue, this size is too small, and continue, and that's not really what we want, because if this is not allocated, and this is not allocated, and this is not allocated, then these together are large enough to hold this 2500. So what I want to do is I want to prevent the situation that we have more than one chunks which are not allocated in a row. Okay? Of course, you can have multiple chunks that are allocated in a row, but I want to prevent the situation that we have multiple unallocated in a row. So if I deallocate something that is neighbors to some free space, then I will merge it again with the previous one. I mean, if the previous one is free, then I will merge this, and if the next one is free, I will merge this. And if both are free, then I will merge this first, so that we have this situation. 2048 plus the size of a memory chunk. And after that, I merge this chunk with this. So this really saves us a lot of cases if we do it like this. If we merge this first and then this, we only need 2 cases instead of 4. Okay. So, how will the situation be when we start? When we start, nothing is allocated. So if nothing is allocated, then I can have only one chunk. Because otherwise, if I had two, these would be two consecutive chunks that are both free, and I didn't want to allow this. So we will start with one chunk with the full size. So this is the first chunk, so its previous pointer will be set to 0. It's also the last chunk, so its next pointer will be set to 0. It will be not allocated and have the full size that we get from the kernel. Okay? And when we allocate something, then we will try to chop off, or then we will try to split the chunk. Then we will set this next pointer here, this previous pointer here. This will be allocated then, this will not be allocated. This will be the size that we have requested, and this will be the size from before minus the size that we have requested. Okay? I think that makes sense. If there is a chunk after that, then his previous pointer is still pointing here. We have to take care of that situation also and move it over here. So this is really nothing surprising if you know linked lists. Just a little bit of working. And yeah, since we really decide the locations of these memory chunk instances, we have to do some extra fiddling that you wouldn't have when you did linked lists normally. But it's not that bad. So let's just program this now. So I will comment these tasks out. Yeah, so on a 32-bit system, the memory addresses are 32-bit. And that is why we set size t to uint 32 here. On a 64-bit system, we would set this to uint64 instead, because then we could dereference 64-bit integers. Okay, the memory manager will have a pointer to the first chunk, but it doesn't have to store the size, because the size is actually stored inside the memory chunk. Okay, so we want to call the allocation later from functions, and functions are static. So like with the interrupt handler, we will have something like an active memory manager. Which we will just set to this in the constructor. Okay. This is how this is going to look. Okay, so in the constructor, as I've said, we will set the active memory manager to this. And then we will set the first chunk to the address that we get here as first. So the start is the offset where the memory manager is going to, the data that the memory manager is going to handle. So this is where we put the first memory chunk. But if the size that we get here isn't sufficient, and this, it might happen, we should really protect ourselves against the situation, because if this situation arises, then we would be writing outside of the area that we are allowed to write. So it's not really it's It's not really likely that this happens, but to make sure. Okay, so the first chunk is not allocated. As I've said, the first and next pointer are 0. Okay. Okay, when we try to allocate something, we will iterate through this list of chunks and look for a chunk that is large enough. So this is really how you iterate through a linked list. So when we find a chunk that is free and large enough, then we set this result pointer to that chunk. And in that case, we can also terminate this loop. Okay, after that, if we haven't found anything, then the result is still 0, and then without paging, then we are lost and we just have to return 0. Okay. Now here, when we reach this line, then we know that the result is set to something. So we can look what I'm doing now is if I find a large chunk, so maybe this is 30 megabytes and I only want 10 bytes, then Yeah, then I chop off 10 bytes and put the next memory chunk instance here. But yeah, what happens if the size isn't even as large as what we've requested plus the size of a new memory chunk? Well, then we cannot split it. Then we would just have some bytes left over here. So the program that requested the data will just have a few bytes left over, wasted. So we can only split this if the requested size plus the size of a memory chunk is larger than the size that has been here before. Is less than. And this +1 that I put there is, if you don't put this +1, then you would split the chunk into the requested data plus only the header for the next chunk, but it would have size 0, and that wouldn't make sense, right? So if the chunk is too small, then I just mark it as allocated. And in the other case, we make a new chunk. And we put that to the position of the result. So here's the result pointer. We add the size of memory chunk to get here, and then the size that has been requested to get to the position for the next chunk. So the result later will get the size that we've requested. And the new chunk that we've cut off at the end will get the size of the old chunk minus what we have requested. Okay, and then we have to modify all the pointers here. Okay. Next becomes, what was the next before? And if there is something, its previous pointer must be set to temp. Actually, we can just move this down here. And flip this. Okay, so if the result is larger than what we need, large enough to split, then we split it. Then after that we mark the result as allocated. And then okay, so the result pointer points to the start of the memory chunk, and now I return this address plus size of the memory chunk, so this is a pointer to the beginning of the region that I have allocated. Okay, so in the free, first, so we have given the guy who requested the memory the pointer here to the beginning of the free region, and this is what we get back when he frees this region again. So we get the pointer here, but we need a pointer to the memory chunk, so we will subtract size of memory chunk from it. Okay, and now we'll do the merging that I've talked about before. So to merge the chunk with the previous one, we set the next pointer of the previous one to the next of the chunk. And also if there is a next one, so we've removed it from the forward linked list, we removed it from the backward linked list. And then we just add the size that we have freed, including the memory chunk, to the size of the previous chunk. And then we move this chunk pointer to the previous chunk. And by this, we now have a situation where we know that the chunk on the left of the current chunk is allocated or not existent. And So what we have done now is we have changed this pointer to go over here, and this pointer to go over here, and we've changed the size. We've added all this to the size of this chunk. And now, before we had the pointer here, and we've changed this also, we've set it now here. So it looks like we have been freeing this whole chunk, and the chunk on the left is allocated. Okay? So this is all gone now. And this is how the situation looks now. Okay? So now we know this is allocated or null. And now we have to look, so the pointer is now here, so it looks like we have been trying to free this, but nothing, but the space on the left of the pointer is allocated. So now we just look into the case that the thing on the right is also free. And then we have to merge this new chunk with the next chunk also. So and here we basically do the same thing. Yeah. So we just increase the size of the chunk. So we swallow the next chunk. Yeah, so if the new next chunk exists, then we set its previous pointer to ourselves. Okay, So this should do everything we need. I mean, it does that in a relatively slow way. You know, if we allocate 1 million bytes one by one, then the next allocation will take 1 million iterations to find some free space. But yeah, I think you will be able to come up with better ways of finding free space, like keeping track of the free chunks and maybe have larger chunks so that I think really this is what a memory page actually is. It's just a chunk with a certain size, and when you allocate some chunk, then you allocate the full page, maybe, I don't know, maybe a megabyte or something, and you assign that to the program that requested it. So when it requests more, then you chop off more from that 1 megabyte, and then you don't have to jump in these small steps. Then you could jump in megabyte steps through the RAM to find a free page. Okay, so let's put this in the makefile. So now I'm going to instantiate one. And the question really is, what values do we pass here? So I will just hard-code this to start at 10 megabytes. What should we use as the size? I mean, we've given the virtual machine 64 megabytes, so we could use just 54 megabytes as size here. But that wouldn't be portable. So what I'm going to do instead, I mean, as far as I know, there is a BIOS interrupt which will give you the size of the memory, but I really don't want to go into interrupts inside the C code, inside the C++ code. So there's actually a better way to get this. So, yeah, the situation is this. We are getting this pointer to the multi-boot structure from grub, right? And so far we haven't done anything with it, but when you look into the multiboot.h from the GNU project, also known as Linux, then you will find this structure here, the multiboot info. Okay, and there you see how this data is structured. So you could just copy that multiboot.h and include it, and then you could use multiboot info pointer instead of void pointer. But for copyright reasons, I'm not going to do this here. What I'm going to do is I'm counting here. So this is 4 bytes. This is 4 bytes. So after 8 bytes, we come to this integer, mem upper, and this really tells us the size of the RAM in kilobytes. Okay? So what I'm going to do now is So I'll take this pointer to the multi-boot structure, add 8 bytes to it, and cast the result to an uint32 pointer. And then here as size, I will just take the content of that pointer, multiply it with 1024 because it is in kilobytes, and I will subtract the address where the heap starts, and I will also subtract 10 kilobytes of padding behind this behind the heap. Okay, so something that I have tried before to really not hard code the heap is I tried to put a pointer here behind the kernel stack and then make it global. And in the kernel I would have extern C void pointer heap. And then you would have to take the address of that heap. But I don't know. I've had all sorts of problems with that. And as I've said, I've really given up on the subject. I'm just hard coding this to 10 megabytes and hopefully we are good for some time. Okay, so yeah, this should be a pointer to a chunk, of course, not to a memory manager. Okay, and now you see the heap starts at 10 megabytes, and here we have allocated something that starts at 10 megabytes plus 10 bytes. Hexadecimal 10, 16 bytes. Yeah, that makes sense. Okay, so this apparently works. As I've said, I've had so much trouble with this, I don't even dare say that it does work. I only dare to say it seems to work. So, okay, yeah. So now we can allocate memory, but only if we have this a pointer to this memory manager, but we have a static pointer to that. So what I want to do now, I mean, on the command line we have deactivated the inclusion of the new operator in from the compiled code. So so we can allocate RAM, but normally we would want to allocate it more in a way like not really getting a void pointer, but we want to get we just want to say, hey, I want a new object of this type. You know, that's the C++ way of doing it. You know, this is very C-like, what we are doing here. So what I'm going to do now is I'm going to the interrupts.h. And here I'm going to include this memory management.h. Wait, I didn't want to do this in the interrupts. I wanted to do this in the PCI. Okay, and then in the PCI CPP. Here I want now to do something like so here I want to set this driver to something like new AMD something. Okay, so I could do it like this. No, actually I couldn't do it like this because I haven't written this new operator. So this is what I'm going to do now. And I'm doing this outside of this myOS namespace. So these are the two versions for new. And for delete. Okay, and I will implement these. basically by just going to this active memory manager. Strangely enough, the other one is just a copy of that. Looks kind of wrong to me, but whatever. By the way, this is a point where we now have a delete operator again. So this is a point now from which on you can use virtual destructors again. Okay? Okay, so if I do it like this, then in this PCI.cpp I can actually just say driver equals new type and give it the parameters to the constructor. But here's a really big problem. So if we don't find any place to put this requested object, this requested memory, then the loop terminates and returns null. Right? It just returns 0. So I'm not sure about this, but I think malloc is apparently supposed to throw an exception if it doesn't find memory. So normally in C++, when you say new, it calls malloc, and if malloc doesn't find anything, an exception is thrown. But we don't have any exception handling yet. So we only can return 0 instead, which is how malloc did it a few years back, if I remember correctly. So, but the thing is now this, if malloc just returns 0, then this new will, since no exception has been thrown, the new will just say, okay, I have gotten something, I will use this. And normally, since you have gotten 0, this would mean you are dereferencing a null pointer and you get an exception, a null pointer exception. That is what would happen in user mode, but we are in kernel mode. And in kernel mode, you have access to the memory location 0. You know, the null pointer is just a pointer to the memory location 0. So if new gets this illegal return value 0, it tries to access it, and in kernel mode it's allowed to do that. In kernel mode you are allowed to dereference a null pointer. So therefore this, you cannot really do it like this. So what you would have to do instead is we need to make two new versions called the placement new. And in the implementation, they just return this pointer. So this is called the placement new operator, if you look for this. This is what you use when you want to call a constructor explicitly on RAM that you have already allocated in any way. Like this. There's also a placement delete for explicitly calling the destructor, but yeah. So this is how that looks. And then inside this PCI CPP, you can do this. So you can allocate the RAM explicitly. So you allocate a memory region of the size of the class that you want to give here, and then you have to check explicitly if this is 0, and only if it's 0, only then you call the constructor explicitly. Like this, new driver AMD, and here you put the parameters. Okay, so we haven't written this class and we haven't defined the parameters of the constructor, but that is what we will do next time. So yeah, so this is all we need to do for the memory management. Yeah, as I've said, it's not really fast, but it does the job and it's a starting point. So as I've said, I think you can come up with better ideas. You probably should be going into virtual memory fast so that you can really work with virtual addresses, and then the processor will tell you if a program tries to access a page that currently isn't in the memory, and then you can do the paging and write some page to the hard drive and load the requested page back into the RAM. But yeah, in my personal experience, I've seen computers really go down on their knees when they start with the paging. So my experience is when the computer starts paging, you're screwed anyways. You're better off rebooting it. So that's why I have never actually written code for paging. But yeah, I mean, for what we are doing with 64 megabytes is sufficient anyways. So so yeah, now you have a heap. Now you can do dynamic memory management, and yeah. Next time we will use this here in the code for the PCI to dynamically instantiate a network card driver, and then we will start talking to the network. So yeah, don't forget to subscribe so that you don't miss the next video when we start talking to the network. If you like this video, hit like, and yeah, see you next time. Bye.